By definition, parallel interface is a circuit consisting of hardware components and accessories that links one device to another, transferring one full word at a time. If there are n bits in a word such as n is equal to 8 or n is equal to 16 or 32 bits, then that many wires are connected between two devices, such that all bits of the word are transferred at the same time. In old computers, usually this was commonly used to connect a computer with a dot matrix printer. Centronics Corporation designed the original Centronics parallel interface for dot matrix printers. It is still a widely used standard input-output interface for connecting printers and certain other devices to computers. The interface typically includes a somewhat cumbersome cable and a 36-pin male and female connector at the printer or other device. The other end of the cable plugs into a 25-pin parallel port on the computer. Data flows in one direction only from the computer to the printer or other device. In addition to 8 parallel data lines, other lines are used to read printer's status information and send control signals. In addition to 8 parallel data lines, other lines are used to read printer status information and to send control signals. In 1981, IBM preferred this interface as an alternative to the slower one bit at a time serial interface for connecting printers. In context of IBM PC, the parallel interface was also called as Centronics Compatible Parallel Port to indicate that it followed the same interface protocol. In all names, it is still essentially a parallel interface. In 1990s, it was standardized as IEEE 1284 or 1284, which defined its first version as Enhanced Parallel Port EPP with unidirectional data transfer from PC to printer. Its advanced version was named as Extended Capability Port ECP, which could transfer data in both directions. When the Centronics parallel interface was first developed, the main peripheral was the printer. Since then, portable disk drives, tape backup drives and CD-ROM players are among devices that have adopted the parallel interface. These new uses caused manufacturers to look at new ways to make the Centronics parallel interface better. In 1991, Lexmark, IBM, Texas Instruments and others met to discuss a standard that would offer more speed and bidirectional communication. Their effort and the sponsorship of the IEEE organization resulted in the IEEE 1284 committee. The IEEE 1284 standard was approved for release in March 1994. The IEEE 1284 standard specifies 5 modes of operation, each mode providing data transfer in either the forward direction, that is computer to peripheral, or backward direction, that is peripheral to computer, or bidirectional, that is one direction at a time, but in both the directions. The computer must determine what the capabilities of the attached peripheral are and which mode to utilize. The concept developed to determine these factors is called as negotiation. Negotiation is a sequence of events on the parallel port interface that determines which IEEE 1284 modes the device can handle. An older device will not respond to the negotiation sequence and automatically compatibility mode is selected by default to operate that device. A newer device will respond to the negotiation sequence and a more advanced mode can be set. The 5 modes permitted under this standard are: 1. Compatibility mode is the original Centronics parallel interface and intended for use with dot matrix printers and older laser printers. the compatibility mode can be combined with the 4-bit nibble mode for bidirectional data transfer. 2. Nibble mode allows data transfer back to the computer. The 8 wires are bifurcated into 2 4-bit buses. One bus takes data from computer to printer or device, and other bus takes data in the reverse direction. The nibble is defined as a 4-bit unit. This mode uses the status lines to send 8-bit data into 2 parts or nibbles in 2 transfer cycles. 3. Byte mode uses software drivers to disable the forward direction drivers and enable reverse direction drivers for data to be sent from printer to the computer. The data is sent at the same speed in forward and reverse direction. This is naturally twice as fast as the nibble mode. 4. ECP mode, Enhanced Capability Port Mode, is an advanced bidirectional mode for use with printers and scanners. It allows data compression for images, first in first out or FIFO buffering for data elements in queue, and high speed bidirectional communication. Data transfer occurs at 2 to 4 megabytes per second. An advanced feature of ECP is channel addressing. This is used for multifunction devices such as printer, fax, modem devices. For example, if a printer fax modem device needs to print and send data over the modem at the same time, the channel address software driver of the ECP mode assigns a new channel to the modem so that both devices can work simultaneously on same set of wires. 5. EPP mode, Enhanced Parallel Port Mode, was designed by Intel, Xircom and Zenith Data Systems to provide a high performance parallel interface that could also be used with the standard interface. EPP mode was adopted as a part of the IEEE 1284 standard. The EPP mode uses data cycles that transfer data between computer and the peripheral, and address cycles that assign address, channel or command information. This allows transfer speed of 500 kilobytes to 2 megabytes per second depending upon speed of the slowest interface. The EPP mode is bidirectional. It is suited for network adapters, data acquisition, portable hard drives and other devices that need higher speed. In IBM PC operating system, the printer port was logically defined as physical device LPT, a short form for line print terminal or local print terminal or line printer. A computer may have more than one printer connected, and they would be named as LPT1, LPT2 up to LPT4. However, they were also generically or logically addressed as PRN, and one of the physical printers connected were assigned label PRN on it at the runtime. IBM provided a 25-pin female connector on its chassis as shown in figure 9. The Centronics compatible printer had a 36-pin female connector on its chassis as shown in figure 10. IBM devised a cable using a 25-pin male connector at PC end and a 36-pin male connector at the printer end, which is popularly called as printer cable or parallel printer cable. Figure 11 shows a 36-pin male to 25-pin male parallel printer cable. Note that the left side connector is 36-pin male connector, which is slightly larger than 25-pin male connector, which is shown on the right side. Centronics compatible parallel port was one of the major and important interfaces of PC at that time, since it offered high speed bidirectional data transfer facility. Various popular devices of these years which used this interface were dongle for copy protection, zip drives, modems, sound cards, webcam, gamepad, joystick, MP3 player and SCSI devices. Let us now discuss the hardware aspects of this standard. We begin with 25-pin connector at the rear of the IBM PC and the signals on it. The pin out of signals on 25-pin connector is shown in figure 12. The basic or older parallel printer interface had following important signals. 1. 8-bit data bus signals D0 to D7, where D0 is LSB and D7 is MSB or most significant bit. The 8-bit word usually was ASCII coded character. In the complete set, some characters were printable text characters, some were special or graphic characters, and some were control characters which manipulated printer's setting and print style. 2. 4 control signals outputted from computer to printer known as strobe, line feed, reset and select printer. Every time the computer sent a new character to the printer, it signaled to printer by pulsing strobe line active or low for a short duration. Line feed output was a setting dictated to printer which would decide whether each carriage return character should automatically cause a line feed or not. Initialize signal when pulsed true or low would cause printer to reset completely and start afresh. Select printer signal was a general purpose enabling signal which permitted printer to start the work. 3. 5 status signal from printer to computer as input known as ACK or acknowledge, busy, select, error and paper out. Every time the printer received a new character, it acknowledged to computer by pulsing ACK line active or high for a short duration. Busy signal was an indication from printer that it is busy printing last given character and it is not available for accepting new character. Busy signal was monitored by computer and when found true, the computer would wait for it to become false. This could ensure that a very high speed computer could work with a very low speed printer reliably without any loss of data. Select signal was a status signal from printer to computer that printer is powered up and is OK to receive data for printing. Error signal was an indication by printer that its mechanism has gone faulty and it is not able to print the character. This could happen when continuous paper roll would get stuck or jammed inside the printer. Paper out was a special type of error signal sent to computer that current paper roll is exhausted and printing should be paused till new paper roll is installed. In addition to above mentioned 8 plus 4 plus 5 or 17 wires, it provided 8 ground wires to connect PC's ground with printer's ground pins. In all, printer cable had 25 wires as enumerated above. The maximum permissible data transfer speed was about 20 kilobytes per second. In EPP version, that is advanced version called as enhanced parallel port, the speed could be increased to 2000 kilobytes per second. The voltage level on signals used in this interface is TTL level, where logic 0 is between 0 to 0.8 volts and logic 1 is between 2 to 5 volts. We will now discuss how PCs transfer characters or data to printer. Typically, the dot matrix printer have a speed of 100 to 300 characters per second. This means that the minimum time between sending 2 characters to printer is inverse of this rate, that is 10 millisecond to 3.3 milliseconds approximately. Typically, a modern PC or CPU can send data on its port at 1 megahertz rate, that is it can send one character every 1 microsecond or even faster. Thus, a PC is several thousand times faster than printer's maximum speed. The following handshake sequence ensure that PC is slowed down to the printer speed so that not a single character is lost. 1. Initially, PC sets pin 17 true, that is high, to select the printer. This will enable printer to become ready to receive a character from PC. 2. Then PC reads and checks that select input on pin 13 is high, that is printer is powered. There is no point in sending a character to a printer which is either not powered or not ready to work yet. 3. It checks that error signal on pin 15 is false, that is low, meaning there is no error in printer. 4. It also checks that paper out signal is false, that is printer has not run out of the paper. 5. Lastly, PC checks that busy signal on pin 11 is 1 or high, which means that printer is not busy and hence ready to receive a character. 6. Now, PC sends its first character. The 8-bit character ASCII code is set as data by PC on data lines D0 to D7. The event of placing new data is followed by pulsing strobe line low for a small duration and making it high again. This duration for low state is typically 1 to 2 microseconds. 7. Pulse on strobe line triggers action inside the printer. Printer immediately makes busy line low or 0, indicating that it cannot take any more characters. It reads the 8-bit code from data lines D0 to D7 and starts printing. This process may take about 10 milliseconds or 10,000 microseconds. All this time busy line is 0 and PC waits for printer to become not busy. 8. After the character is printed, printer makes busy line false or high and pulses acknowledge line high for a short duration. Note that strobe is a pulse from PC to printer, while acknowledgement is a pulse from printer to PC, confirming that it has received the character sent. 9. Now, the PC becomes free to proceed to send the next character, and it again checks as per condition given in steps 2, 3, 4, 5. If everything is all right, it sends next character and so on until all characters are printed. 10. If paper runs out or jams or ribbon is stuck or printer has no power, then one of those conditions become true and PC pauses for that to be rectified or sorted out. Note that for how much time a busy signal is kept on, that is in true condition, depends entirely on the speed of the printer. A fast printer may keep busy signal true for 3 milliseconds, while a slow printer may take as long as 10 milliseconds. This way, the printer is able to slow down the PC to its maximum speed and both work in a synchronized form with PC without losing a single character. Printer manufacturers soon understood that most of the print jobs had a short length of 1 or 2 pages. Note that typically each page has about 80 columns and 25 rows and can take about 1000 to 1500 characters. So, they added electronic memory or buffer memory inside printer of say 2048 or 2 kilobytes or more, which could hold that many characters in a first in first out FIFO queue. This memory was very fast and could absorb data at a very fast rate, typically 5 microseconds per character. So, whenever the PC would send the data to the printer, it was actually sent to very fast buffer memory inside the printer, and thus the PC could fill it at an extremely fast rate. The printer memory was so designed that it could accept the data from PC at a fast rate, but send data to print mechanism at a standard slow rate. So, the buffer was emptied at a slow rate. If PC had less data than the buffer capacity, then it would dump its data into buffer and get released very early. If the data to be printed was larger than the buffer memory, then PC would send data to buffer memory initially at a fast rate, and the buffer would become full. It will wait till buffer had a space to receive next character. In all, this arrangement saved some of the PC's precious time, and it was considered a great improvement over printers which did not have a buffer. The parallel interface or printer port was so popular that a variety of printers available over 20 to 30 years, such as character printers, line printers, ball printers or dot matrix printers, all had the same interface to receive data from PC. They had a variety of features, sizes and speeds, but they all communicated with PC using above mentioned sequence. Eventually, USB interface replaced parallel interface as a favorite interface to communicate with printers and became extinct like serial interface.